So when we break down the computer vision in this fully autonomous world in which driving assist becomes a special case, we have the detection, we divide them into 4 buckets. One of them are about road users. Detecting all vehicles and other road users with cyclists and pedestrians and people on scooters and whatever, road users. These are dynamic objects. And this area is very, very rich in terms of how you specify it. And I'll show some more details about it. Then there is road geometry, everything about the drivable paths that we see. So it's not only the lane marks. We need to break down the scene into drivable paths and understand what each drivable path means. Then there's road boundaries. All the delimiters, could be a curb, could be a guardrail, all the delimiters that we find on the road. And then the road semantics. What can we infer from a semantic point of view from the information that we see? This is traffic signs, traffic lights, pavement markings, and so forth. So these are the 4 buckets. Now comes the task of reaching the 10 to the power of minus 4. This is an incredible number. So the way we approach this is we create internal redundancies. These redundancies are not statistically independent, but take, for example, vehicle detection. Rather than building one humongous black box network, deep technology for detecting vehicles, we do it multiple times using different algorithms. These are these internal redundancies. And each one of those algorithms is end-to-end. So it doesn't rely on other algorithms. So in this way, again, we don't need to prove ourselves statistical independent. It's just a software design approach to do the same task using different approaches, but each approach doesn't rely on the rest. So the way we look at it, there are several sources of information. One is appearance. You have pixels in the image. This is appearance. A vehicle has an appearance, a typical appearance, and you use that typical appearance in order to train a network to detect the vehicles, for example. Then there is geometry, things that we find from perspective, from motion, all sorts of classical things that we as humans use in order to extract 3D, even though our sensor is 2-dimensional. Our eye is a 2-dimensional sensor. Camera is a 2-dimensional sensor. We see 3D implicitly. We extract 3D information, we infer 3D information. We don't have direct access to 3D information. This is called geometry-based. So the same thing for detection and also for measurement. Measurement meaning lifting the 2-dimensional information to 3D. Because in order to control the vehicle, everything needs to be situated in a 3D environment. So we need to lift all the 2-dimensional detections into 3D. And here also we have appearance and we have geometry. And again, the idea is to use them as separate tracks, not combining all this information into one algorithm, but using separate tracks. So let me give you an example. Let's look at, I'm going to focus now on road users. So let's look at, there is a bus, a white bus here in the scene, and we're detecting a road user using 6 different algorithms. One of them is the classical pattern recognition. You're detecting a 3-dimensional box situated on a vehicle. Using pattern recognition, so you train a network that scans the image and tries to find an area which you can put a box around it that will fit the appearance of a vehicle. This is the classical, when people talk about vehicle detection, they normally refer to this. There's another one which you call full image detection. Say you have a large truck or large bus very, very close to you, a few centimeters away from you. This is not something that easily putting a bounding box on it. You need to approach it differently. It's still appearance, but it's a completely different algorithm on how to handle very, very close objects, and I'll show you some examples later. Then we have a free space. We call this top view free space. So the green, all these pixels of green is where the road is, and whatever is not road is suspect to being an object. So this is another way to do object detection. Then we have features like wheels. We use them also separately to define objects. Then we have what is called in the academic environment Lidar. So it's kind of Lidar, but with cameras. So the fact that we have multiple cameras, we can use it in order to generate a three-dimensional percept of the world using triangulation, classic triangulation, but we have multiple cameras in the car. And then we can feed that data into the Lidar processing algorithms. As we said, we have two separate streams. So we have already algorithms that take Lidar information and create an environmental model. Instead of feeding it Lidar, we feed it the information coming from this stereoscopic multi-camera stereo. Okay? So this is completely different track, both for detecting objects and measuring information. So rather than developing an algorithm that takes all these sources of information and outputs the objects, we have 6 different algorithms in order to create those internal redundancies. The same thing for measurement. I want to lift from 2-dimensional to 3D. The Lidar, of course, gives me 3D information. The visual road model using classical computer vision of plane plus parallax, perspective, optic flow. We can get a road model and use that in order to get depth. We have a map, an HD map, which we build using our REM technology that also gives us information about the shape of the road, which we use to extract the depth. And we have another network that uses appearance in order to estimate range. Okay, so each one of them is a separate track rather than combining them all together. We have different engines to create the lift from 2D to 3D. And again, what's underlying all of that is reaching this 10 to the minus 4 probability, right? Because it's not enough just to show we can do autonomous driving. We have to do it in a way that at the end, when we put all those streams together, we can get a very, very low probability of mistake, which is at least as good as humans, but much better than humans. Has to be much better than humans. Okay, so now let's go examples of each. So this is the full image detection. If you look here, when the object is very, very close to you, it becomes a very big challenge on detecting it as an object, because there's really nothing here to say that there's an object. Let's look at this as well. Now, this is important when you are maneuvering in autonomous driving situation, when you're maneuvering in very narrow situations. It's a two-way road, there's oncoming traffic, there's blockages, and now you are driving and the other road users are centimeters away from you. Okay? So it's a completely different approach on how to detect an object. Let me show you an example of how this looks like. So what you see here, this is the top view from the system. We're getting closer to a blockage, and now you can see this vehicle coming in here, and very, very close. These are the kind of situation in which you need this full image detection and passing through, and you can see this is really autonomous. This is a drone view. I'll show plenty of more examples. So this is one of them. Another is how do you track objects among cameras? So this is a network that uses what is called a signature. This is a technique from face recognition where you take an image of a face and you map it into a vector of numbers, which is called a signature, and that vector of numbers is invariant to facial expressions, whether you change your hairstyle and so forth. So the same thing is being done here, where you use a signature of an object and find that signature in other cameras, so you can track very, very long baseline tracking of objects. This is RangeNet, so using appearance in order to estimate range. So what you see here, this is the classical way of measuring range using some Kalman filtering, so it stabilizes over time. This is number of frames. And the red bar is the true range, and you see here we're using a RangeNet, using the appearance to estimate depth. We can get immediately the range from a single frame. So this doesn't come instead of the classical. This is on top of the classical. Then another engine is pixel level segmentation. So we can see here that every pixel is segmented. The color of the pixel is what it is. So green, it is road. And you see here delimiters like a road edge are in red. Let me run this again. And what you see below is a segmentation into objects. So each color is a separate object. Here we're coloring only the road users, so the cars and the pedestrian. Let me run this again so that you can see. So this is the pixel segmentation. So every type of object has the same color. And here, this is the object detection. So every color is an object. And this is the same thing at night. So again, so this is a stream running parallel to everything else in the system. This is not an engine that is combined with other engines of the system. This is a completely separate subsystem. This is from the surround camera, so same thing being computed from every camera. Then we tell ourselves there are certain objects that occur frequently. Those objects that occur frequently would like to have a model-based detection. So to train a network for that particular class of objects, like doors. A door is tricky because it's hovering above the ground plane. So to get measurements of something hovering above the ground plane is tricky when you talk about cameras. And it's sufficiently important from a safety critical point of view that you want to do something dedicated for it. So you can see that doors are detected as a separate class of objects. And on the right-hand side, you can see how it is you see the red point here. This is the door, and how the autonomous car is maneuvering its way around the open door, calculating a new trajectory in order to bypass the open door. Another separate class of objects are strollers. You can see here the stroller is sufficiently important from a safety critical point of view. Last thing that you want to do is to hit a child. So it warrants a separate detector. And you can see on the right-hand side an example of a stroller coming in, and the autonomous car is taking notice of it. Then comes another engine. This is the parallax net. So this is using geometry. So every pixel is now colored based on the height from the ground plane. So red is above the height plane, blue is below the ground plane, and the ground plane is not necessarily a plane. It could be something that is curved, and this is a network that is trained also on moving objects. So it's not only stationary world. So again, this is a separate engine that is used for measurement and it's used also for detecting objects. Because if something is above the ground plane, at least you know there's something there before you even know if it's a car or not a car. Then there is what we call we didn't coin this name. It's in the academic circles. It's called the Lidar. So it's a deep network that takes the multiple cameras that we have in the car and combines them all together to do triangulation and get a dense 3D percept. There are many uses for it. One of them, there are all sorts of hovering objects, protruding objects that you need to know about, and so you need precise 3D. So these are examples of the cameras that their images are fed into this kind of network, and then when you look at it, you get a 3D percept just like from a Lidar, but much higher resolution because we're talking about the cameras from the existing cameras in the car. So it's not that we have stereo units. We have 12 cameras around the car, so it's a long baseline stereo in the academic circle. Here's another clip while we're moving. So again, so this is now a separate route, a separate engine. It's not combined with all other engines that I mentioned before. It's a separate engine that can be used for detecting objects and also measuring a range to those objects. And here is an example how we use the Lidar data and feed it into the Lidar processing stream that we have in order to detect objects. So we take the same algorithms that we have with the vehicle with radars and Lidars and feed it with the Lidar information rather than with the Lidar information in order to get a stream where we detect objects and measure range to them. Here we can see how these different type of streams of information help us to avoid, to define obstacles. So here is a route in which there are many cars that are obstacles. And the system needs to figure out whether it's an obstacle that you need to overtake or whether it's a traffic jam that you need to simply wait that it is cleared. And it's kind of tricky because your view is limited and the object, which is the obstruction, is occluding. But there are all sorts of tells, like if you do a pixel labeling and you know the pixels of the road, you see pixels of road behind the obstruction, so you know it's not a traffic jam. So it's putting all this information together in order to understand what are obstacles and overtake them. Then there's semantics, knowing about blinkers, emergency vehicles, knowing what pedestrians are doing. Let me run this again, because at the beginning we see what this is. Okay, so we know the orientation of the pedestrian. We can go deeper than that and also understand hand gestures, so to know what it means. Come closer, you can pass, stop, I'm on the phone. All of this is also part of the system as part of semantics. So now let me put all of this together. And I'm going to show you a clip from our autonomous car. Again, so we're talking about this stream with only cameras. So it's a car fit with 12 cameras. It's 8 long-range cameras and 4 parking cameras. In terms of the cost, it's really nothing. It's hundreds of dollars. And it's all running one IQ5 chip. The hardware has 2 IQ5 chips, but right now what is being processed is only one IQ5 chip. So it's one IQ5 chip. Just to give an idea what this means. Everybody talks about chips and so forth. So an IQ5 chip has 2 dies. Each die is a 7 nanometer process. It's 45 millimeter square area. So we're talking about a 90 millimeter square area running what I'm going to show you. So 90 millimeter square for a chip is nothing. You know, all these humongous chips that, you know, Xeons and others, these are hundreds of millimeter square chips, hundreds, closer even to 1,000. So we're talking about very, very small footprint, very, very lean compute, going to do what I'm going to show you right now. So this vehicle, 12 cameras, one IQ5 chip, taking all the information from the cameras and doing an end-to-end autonomous driving. Now, we are developing this with the mindset of being able to be agile as a human. So it's not only from an algorithmic point of view, there's also our model of safety, which is called RSS. I'll say a few words about this later. Putting those together enables an agile driving. Now, agile driving is very, very important because the first use case of autonomous driving is going to be robotaxi. Before we can go and purchase a car, it's going to be robotaxis for a number of years. Now, robotaxi is a business. As a consumer, you go and hail a robotaxi, and it should take you from point A to point B. Who is going to hail a robotaxi knowing that it's going to take twice as time to reach its destination? So it has to be agile. It has to drive like a human. So this is in the center of Jerusalem. The driving style of Jerusalem is Boston plus, I would say. So it's really challenging. People are not patient. So if you want to merge into traffic, you need to show your intent, and you need to be serious about your intent. Just turning the turn signal wouldn't do it, right? So, okay, so now, let's have a look at this. So we have here 3 panes. This is from a top view. This is a drone. This is the autonomous car. You see here the Intel Mobileye logo. This is what the computer sees, kind of 360. And this is just to show you that we're not cheating. It's really autonomous driving. Okay. This is sped twice as fast, because in a presentation I want to finish this fast. So here's the autonomous car. So you can see that, you know, it's a very narrow corridor, oncoming traffic, and it needs to find its way. So it's a 1-minute clip, so it will be over quickly. And now it's going to enter into a unprotected left turn. And now see what's going to happen. Okay, now we're showing you the pixel labeling. So this huge bus simply stops. Okay, so now there's occlusion. So what do? It needs to do an unprotected left. So now it's pushing its way. Now there's a pedestrian coming. You see this pedestrian, right, moving its way. This is Jerusalem. Okay, and has to push its way through. Okay, and so we're talking about a system with a bill of material about $1,000. That's what you see the proportions about it. And And this is one stream. There's another stream of radars and lidars that at the end of the development will be put together to reach a 10.-7 probability. Okay, I'll skip this. So in order to show that we're not simply taking a section of few seconds out of 10,000 unsuccessful sections and showing you only the successful section, we put this morning the entire route. It's a 20-minute ride, starting from Mobileye, ending at Mobileye into the heart of Jerusalem. It's available, it's in 4K, so, and it's in original speed, so it's not fast-forwarded, so you can see everything. You can see the strength, you can see the weaknesses. I don't think that there are weaknesses, but if there are, you can see them, and for all to see, right? So it's, I think it's very, very powerful. I've seen this morning a discussion in Reddit, pages and pages and pages of discussion. I think this is what the industry needs, to be transparent, to show what we're doing, and not to be shy about it. So it's all, the entire route is available at the YouTube, in our YouTube channel.